Thank you, good morning, and welcome to the AI Summit Conference. We all know that we're living in a time of an artificial intelligence and big data revolution. Hardly a day goes by that we don't see another article on the web or in the print media. But let's take a look at where that comes from and what it means for all of our companies. The big data and AI revolution is because we have more data than ever before, and more and different sources of data than ever before. Social media, the Internet of Things, these supercomputers called smartphones that we all carry in our pocket. And inexpensive storage means that we have the ability to store this data for later analysis. More powerful compute capabilities and sophisticated algorithms mean we can do incredible things with this data, things that would have been magic only a few years ago. And increasingly powerful algorithms allow us to pull subtle relationships out of this data that would have been hidden previously. There's many implications of this AI and data revolution. Data mining and machine learning algorithms allow us to answer questions that we hadn't even thought to ask, to see subtle relationships, and to predict the future. Clustering and segmentation algorithms allow the hyper-personalization that we all take for granted now in e-commerce. Whereas in the past, the best we could do on large populations was aggregate statistics, now we can identify clusters of similar individuals and act on them. We're seeing increasingly powerful techniques that allow computers to access what many of us call dark data, the unstructured and semi-structured data that was previously hidden from computers. We're seeing the rise of probabilistic and statistical approaches that in many cases are more accurate than the deterministic approaches they're replacing. And this is because of the massive amounts of data they're able to access. And we're seeing the pervasiveness and ubiquity of computer vision, touching almost everything we do online and in the real world. I'd like to concentrate on a few themes, a few consequences of this revolution. I want to talk about some techniques that are making dark data more usable for companies and others. I want to talk about the implications of the rise of computer vision. And I want to talk about how contextual and human-centered design are allowing for user interfaces that help us to get information that recognizes what we're doing at the moment and what we were doing a moment ago and will be doing in the future. And then I'd like to share with you a few examples of partnerships that are enabling impactful innovation in these areas. First, I'd like to tell you about something called Deep Dive, a program developed by my colleague Chris Ray for making dark data easier to use. Many data sources contain different kinds of unstructured and semi-structured data that computers have a lot of trouble accessing. We're all used to relational databases or flat file databases and spreadsheets that computers can access readily. But computers have a lot more trouble with free-form text, and they have yet more trouble with charts and graphs and tables and figures, the sorts of things that populate financial reports or our company's internal proprietary memos or scholarly journal articles. Deep Dive is what we're calling a dark data inference engine. And it enables organizations and others to get more benefit from this dark data. It extracts structured data and creates a knowledge base from these unstructured and semi-structured dark sources. Let's take a look at how it works. There's two critical pieces of input for the Deep Dive engine. The first is the input document corpus, whatever that might be. It might be your company's proprietary memos accumulated over many years. It might be the web. It might be the technical literature in a particular area of interest. And the second input is the target schema. If we think of a database as an Excel spreadsheet, this would be the labels on the columns of that spreadsheet, the attributes or features that you're interested in, And then Deep Dive is going to populate the rows, the records of that spreadsheet. And that, in fact, is the output knowledge base from Deep Dive. It looks very much like a spreadsheet, a very large spreadsheet. But then critically, there's an iterative loop that allows the user to tweak that input target schema and to correct errors. This works so well that dozens of companies worldwide and hundreds of researchers worldwide are now using Deep Dive, which is available as open source, and applying it to their work. Surprisingly, it's even more accurate than human experts in their respective fields. DARPA, the Advanced Research Projects Agency, has applied Deep Dive to fight human sex trafficking on the web in their program called MEMX, that some of you might have heard of or remember when it was profiled on the American TV show 60 Minutes. The same properties of the web that make it an important asset for legitimate commerce also make it useful for human sex trafficking, people selling guns, drugs, and so on. In this work, the researchers crawled 35 million websites that appeared to be advertising female sex services and tried to turn the ads against the human traffickers by using the very data in the ads, phone numbers, geographical areas, names, services, prices, to try to identify which ads corresponded to human trafficking, and then to identify the traffickers. This is working so well that law enforcement officials are now using this data for investigation and prosecution, and the New York District Attorney is further along than any in the country in using this for their investigations and arrests. Computer vision is becoming pervasive and ubiquitous, touching everything we do, and now doing so much more than just tagging objects in images on the web. And this is the story of a few of my colleagues, Stefano Ehrman, David Lobel, and Marshall Burke, who wanted to see if computer vision could be used to help measure and fight poverty. The reduction of poverty is the #1 United Nations Sustainable Development Goal. But to reduce poverty, we have to measure it and measure our progress toward eliminating it. The traditional methods of surveys are to send people with clipboards or tablet computers from hut to hut and village to village in some of the least developed parts of the world. This is expensive, it obviously isn't scalable, and the spatial and temporal resolution are poor. These researchers wanted to see if they could take advantage of satellite imagery, which is now widely available and low cost, to do this same thing. But the data in satellite images is unstructured. The usual approach to this, as all of you who do deep learning know, is to have a training data set with labeled images. In the developed world, we have lots of labeled images. But in the resource-poor parts of the world, where the researchers wanted to measure poverty, that kind of data is scarce. As a result, there wasn't a good training set to go from satellite images directly to measures of poverty. So they wanted to see if they could use a technique called transfer learning that substitutes a different but related measure for the desired one. And in this case, the proxy that they were using was nighttime light intensity. In other words, nighttime satellite images. The idea was to see whether they could use nighttime satellite images to train a convolutional neural network that was interpreting the daytime images. And then if they could transfer that network to go from daytime images to poverty. Here's a nighttime satellite image of the Korean Peninsula. The bright area in the lower right is South Korea, one of the wealthiest and most developed nations on Earth. The dark region up and to the left is not an ocean, as those of you who know geography will appreciate. That's North Korea, one of the poorest nations on the planet. And so you can see at a glance the stark difference in nighttime lights between a rich and a poor country. And so the idea was to use this to train the neural network on daytime images. One of the frustrations that many people have with deep learning is that it's hard to understand what the machinery of the neural network itself is doing. But in this case, the researchers wanted to take a look at one of the intermediate layers in the convolutional neural network and see if it was possible to get some intuition out of it. The top row here is 4 satellite images, respectively from urban, rural, waterway, and roads. The middle row is one of these intermediate layers of the neural network, where you can see the activation map being applied to these images. And then the bottom row is the superposition of these. And you can see that in an unsupervised way, without any human interaction, the neural network is learning to recognize the characteristic features of urban areas and of rural areas and waterways and roads. This has now been applied to several African countries where it's more accurate than the best available baselines. And the researchers hope that by continuing to expand the use of this technique, they'll be able to get better data and more accurate and dense data. We've all had the frustration, whether it's dealing with mapping software or a search engine or something else, that these amazing computers and user interfaces are generally ignorant of what it is we're trying to do at that moment, what our goals are, what we hope to be doing a few minutes from now. Even the mood we're in, are we frustrated, are we anxious, are we relaxed? And increasingly, researchers believe that the key to this is more contextual and human-centered design. And here I want to talk about some work applying that to the design of a new generation of robotics by my colleague Usama Khatib. Usama believes that in the future, robots must be semi-autonomous robots, and that we can then use those to handle dangerous situations, to assist us when greater strength or precision is needed, to cooperate with other robots, or to help us when we're injured or getting old. What all of these applications have in common is that they're complex and unpredictable. And so in contrast to the fixed industrial robots of the past, where robots had precisely calculated trajectories, we're now looking for robots that can perform tasks more the way all of us do, where as we move, we learn, we plan, and in an interactive way, we can handle unpredictable and complex tasks. If this can be done, we can have robots deal with man-made and human and natural disasters like Fukushima. Perhaps we can send robots into the deep sea to repair oil rigs. Perhaps robots can start taking over tasks like underground mining of minerals. Most recently, they created a robot that they call Ocean One, which is a semi-autonomous undersea robot. And in the left-hand image, you can see this robot swimming in the French Mediterranean a few months ago to explore a 17th century shipwreck. The robot's at a depth of 100 meters, a depth that would be difficult for a human diver to spend much time at. It's not a difficult depth for other robots and submersibles, but generally the best those can do is take pictures with a camera. But note that the Ocean One robot has arms and hands. And in the right-hand image, you can see the semi-autonomous aspect of this. On the surface, anywhere in the world connected over the internet, the users are able to see what the robot is seeing through imaging sensors on the robot and three-dimensional displays. Through sensors on the robot's fingers and a haptic interface, the users are able to feel whatever the robot feels. And in fact, this robot was able to recover an intact ceramic vase from the 17th century and bring it to the surface. You can imagine that historians and archaeologists are having a lot of fun with this. These sorts of disruptive factors in AI and data science are touching every one of our industries. Some of us are using these techniques for greater operational excellence and efficiency. Some of us are using these to improve our products and services, or to create entirely new products and services that might have been impossible a few years ago. Some of us are even developing entirely new business models. These sorts of techniques allow us to move into adjacent industries as traditional silos between industries are broken down. But of course, this also means that we face new competitors as companies from those adjacent industries, or entirely new entrants that might be large companies or startup companies, start to compete with us on our home turf. Imagine the poor auto industry executive who woke up one morning to realize that his fiercest competitors are a search engine company and a consumer electronics company.